This is a video for inference for two means, a two-sample t-test. Now in the last chapter we did mostly one-sample tests where you compare one sample to some population number, but a lot of times you're just going to compare two samples to each other, which is actually more common and a little bit easier statistically because you don't need to know anything about the populations. You just compare the two samples. So we kind of started to deal with that where we talked about match pairs procedures, and that allows us to perform inference on two sets of data that are the result of a match setting where you find the difference of the two. But sometimes we're going to have means that come from two independent populations. So for example, let's say we wanted to compare the average ACT mass score for males to the average ACT mass score for females. Or how does the blood pressure for an experimental group taking a new medication compare to that of a placebo group? Questions like this can be answered through the use of two-sample procedures. So of course, the basic start is that we have some different formulas and some different things that we need to talk about. So in a two-sample T procedure, the degrees of freedom get a little tricky because you got two different samples. So there's two ways that you can do this. Okay, one, you're going to use the smaller n. And in that case, the degrees of freedom will be n minus 1, whichever n is smaller. That's kind of like the safe bet. As we've been talking about, the bigger the sample size, the more normal the graph, and the smaller standard deviation. So we can't really overestimate. That's why we pick the smaller n. The second way that you can get the degrees of the freedom is from a calculator. It's a much more complex calculation. Your calculator does it for you instantly. Okay. The standard error in this case is going to look nasty, but it's not that bad once we start plugging some stuff in. So it's S1 squared divided by N1, and it's S2 squared divided by N2. Now, you notice the little subscripts 1 and 2 because we have two samples here, sample 1 and sample 2, so we're going to have to use subscripts to decipher between which sample we're talking about. We're talking about the first sample or the second sample. Now, you can use numbers or you can use letters. Sometimes the letters are a little bit easier because they stand for something in the problem. Okay, a confidence interval. Formula for confidence interval is this. X bar 1 minus X bar 2. Again, that's the difference in the two X bars, plus or minus T star times the standard error, which is S1 squared over N1 plus S2 squared over N2. And again, the degrees of freedom in this case, you're going to use the smaller N minus 1. Okay, so when we test a hypothesis, the null hypothesis in this case is always going to be mu1 equals mu2. Remember, null hypothesis, HO means no change. If there's no difference between the two samples, then they'll be equal. The two-sample T statistic is this. T equals X bar 1 minus X bar 2 minus mu1 minus mu2, that's the difference of the means, all that over our standard error, S1 squared over N1 plus S2 squared over N2. And again, that looks pretty nasty, but once you start plugging in, you'll realize it's not too bad. Now, this is really nice because mu1 minus mu2, again, if there's no change between the two, it's going to be 0. So that part of the formula really is just going to cancel out and be 0. Now, the hypotheses, or the alternate hypotheses that you test, are always going to be one of the three. Either mu1 less than mu2, either mu1 greater than mu2, or mu1 not equal to mu2. Okay, and we're going to do a lot of practice with this because these do take a little bit more time to get used to than the other problems. Okay, so here's a problem. Education and law enforcement. You obtain the number of years of education from one random sample of 38 police officers from St. Pete and the number of years of education from a second random sample of 30 police officers from Largo. Okay, so there's St. Pete, there's Largo. The average years of education for the St. Pete sample is 15.4 with a standard deviation of 2 years. The average years of education for a Largo sample is 14.1, standard deviation of 2.5. Is there significant evidence to conclude that the mean number of years education in St. Pete is greater than Largo? Okay, so I'm going to go ahead and list some of this stuff to help us out. Okay, so mu sub S is the mean education for St. Pete. Mu sub L is the mean education, number of years of education for Largo. Okay, so for St. Pete, we had an X bar S. Now, instead of using 1 and 2, I'm going to use S, so anytime I see it in the problem, I know that that S stands for St. Pete. So X bar S is 15.4 years, and again, I got that from the problem. Okay, standard deviation of St. Pete, SS, equals 2 years, and NS equals 38. All right, the mean from the sample of Largo, X bar sub L, was 14.1 years, and S sub L was 2.5 years, and N sub L was 30. Okay, so I'm just copying that down so you can see the hardest part of this problem is really identifying what those variables are. Once you identify those, it's really just plugging and chugging. Okay, now, so we have our same 4 steps, hypotheses. Okay, null hypothesis, no change. If there's no change, mu sub S will equal mu sub L. Now, in the alternate hypothesis, it says mu sub S, St. Pete officers, okay, are greater than Largo. So I can just mu sub S, the mean education level for St. Pete is greater than the mean for Largo. So there are my hypotheses. Now, I already took care of what mu equals in words right above that, so I don't need to write that again. Okay, conditions. Now, these conditions are a little bit more tedious because I have to check both. So, both come from an SRS. Alright? So that's that's simple random sample. We have normal, NS greater than or equal to 30, and NL greater than or equal to 30. So I really have to check both of those. 38 is greater than or equal to 30, and 30 is greater than or equal to 30. So both of those are okay. The central limit theorem applies. And independence, I don't even really need to check it like I did before. They're independent of each other. 2 samples are independent of each other. Okay, so we're assuming that the level of education for St. Pete really doesn't affect the education levels for Largo. Okay, now, my favorite part, the calculations. Okay, so in the calculations, we're going to write our formula out. T equals X bar L, whoops, let's do S, minus X bar L over standard deviation of S squared over NS plus the standard deviation of L squared over NL. Now, we do have this part, I'll write it in black. It ends up being 0, so I don't end up writing it mu S minus mu L. Again, we're assuming that that equals 0, so we don't really need that as part of the formula. Okay, so off to the side here, I'll calculate this just to show you. X bar S minus X bar L equals 15.4 minus 14.1, which gives me 1.3. So that means, on average, St. Pete police officers had 1.3 more years of education than Largo officers. All right, so I'm going to plug those things into my T formula. T equals 15.4 minus 14.1, which we know is that 1.3. That's the difference between the two, over the square root of SS squared, which is 2 squared, over 38, plus 2.5 squared over 30. So again, I'm matching up the standard deviation of the St. Pete 2 over squared over the n of the St. Pete, okay, which was 38, and then 2.5 squared over 30. Now I can type that right in my calculator, just like that. 2 squared divided by 38 plus 2.5 squared divided by 30, and that will give me the standard error, which we're just going to call 0.56, because that would round up. Okay, so the standard error in this case, so this would be 1.3 divided by 0.56, which is going to give me a t-score of 2.32. Okay, now to get the p-value, the degrees of freedom is 30 minus 1, 29, because that's the smaller sample size. So to get the p-value, I'm going to use TCDF 2.36, comma 1 and a bunch of zeros, comma 29, and get a p-value of 0.0126. And from that point forward, it's just the same as the other problem. So once we get down to our conclusion, let's use alpha equals 0.05, unless it said something different, which I don't believe that it did. Nope, so we'll use 0.05. Okay, we will reject the null hypothesis that mu s equals mu l. Again, if there's no difference, then the education levels of the two will be the same. At alpha equals 0.05, significance level, since the p-value is less than alpha. 0.0126 is less than 0.05. And finally, we have significant evidence to prove the the mean years of education for St. Pete police officers is greater than Largo police officers. Okay, so that's the problem. I know what you're thinking, that they're long problems and they're a little bit more tedious than the other ones, and they certainly are. But once you get the hang of it, you realize it's the same overall process. You just got a few more things that you got to keep track of and plug into the formulas. And of course, some of you will jump ahead and look for how to do this in a calculator. You can. It's a little bit different, and that's something that I will go over in class so that I can make sure that we're all on the same page.